Okay, so where are we? Or deleted anything? Right. So first, let's look at the condition. Let's look at this particular condition, right? Mm, okay, first let's look at this condition. So this box represents power system, right? And we have one device with some reactance. And the current is being injected from the device. So, okay. So see, suppose if they are saying that X is supplying power, right? They're saying X is supplying power, then we are going to assume this generator convention. So we discussed there are two conventions. One is generator convention and one is load convention. So if you see in here in the diagram, they have marked the arrow into the system, and they're saying X is supplying reactive power. So we are actually going to use generator convention, right? So if it is supplying reactive power, suppose if it is supplying reactive power, there are two possibilities. If you remember what we looked at. So supplying reactive power money. Power means two possibilities. First one is supplying lagging VR or consuming leading EAR, right? So what does that mean, right? So the direction of current. So basically, both are interchangeably usable, but if you see here, since the direction of current is into the system, we prefer to say supplying lagging VAR, right? So if somebody says supplying lagging VAR or consuming leading VAR, it is the same, right? Then let's look at the next condition. Here current is being drawn from the system, right? So basically, if current is being drawn from the system, it is likely that X is a load, right? So it is a load. So this is consuming reactive power, right? Which means consuming lagging VAR, right? Or is equivalent of leading VAR. So what happens is that in our system, most of the things actually comes under this category where it consumes reactive power and it is actually drawing VAR. So an example of such thing can be an underexcited synchronous motor. Synchronous machine actually, an underexcited synchronous machine or it could be an inductive load, or could be an induction machine, induction motor or induction machine, right? Or it could be even a transformer. What happens is that also if you see here, why this is the beauty of it. Like see, it's under excited. So basically, your synchronous generator needs some magnetic field for the conversion, right? To set up the magnetic field, and we need that energy. Usually, that magnetic field is set up by the exciter circuit. But if the exciter circuit is not at the proper setting, then it needs more energy or power, more power to set up that magnetic field. So what happens is that we will draw that power to set up that magnetic field. So an under excited under excited. Okay, given an under excited situation, synchronous machine also needs additional power to set up the magnetic field. So it acts as a consumer of lagging VAR, right? Inductive load needs to set up the magnetic field, and induction motor needs to set up the magnetic field. Even transformer needs to set up the magnetic field, right? So it actually tends to draw power for that. That's just what we call as um, reactive power. This is at least what my understanding is. I don't think you will find it in a textbook, but I think this is at the end of the day a possible explanation for that imaginary component in the complex expression for power, right? Then you think of it, if the machine is overexcited. So if the synchronous machine is overexcited, right? What happens? It has more power that is being more than what is required to set up the magnetic field. So that power will be pushed into the grid. So it will be plus, right? Is that clear? Does that make sense? Yeah. So we'll discuss the capacitor part. So when you look at a capacitor, right? Varun, what is the question that you had regarding the capacitor? Sorry, I did not see the message. I saw the message right now. Actually set up the pop-up thing, but I don't know, it did not come up. Yeah, pop-up also chat. But you had some question, Varun? Okay, all right. So if we are talking about a capacitor, we're talking about setting up the electrostatic field, right? So it needs, but that since the current is leading, that power drawn is opposite to the kind of power drawn to set up the magnetic field. That's how we kind of tend to manipulate the reactive power in the system, right? And then let's look at transmission line, right? So what do we know about transmission line, right? Look at a long transmission line, right? We have a capacitor, very small resistance, R, L, G. This is what G would be 1 by R of, right? This is, so when we are studying reactive power, right, R and G does not contribute much. So let's just simplify this into a smaller circuit, right? So it becomes a small LC circuit. Am I audible? Thank you. Okay, so if you see this, okay, so let's simplify this into the circuit. So this is the load. So this is L, this is C. We have IL flowing like this, and we have IC, and we have I load, right? So usually IL will be in terms of amperes. What would be XL in terms of? It will be terms of milliohms. Why? Because L is usually in terms of millihenry, right? And XC would be in terms of mega ohms. Not milli, it will be mega ohms. Why? Because capacitor is usually in the terms of UF, right? And what would be IC? IC would be IC is V by XC, right? And IL would be so previous slide. So sure. Okay. So IL is what? I load plus ICS. Now just give me a second, guys. Yeah, sorry. Okay. Right. So I load is ICH, right? Uh, so ICH is going to be very small because if you see VS, what will be in terms of 220 kV or will be in the terms of kV, right? And XC will be in terms of mega ohms, right? So at the end of the day, IC would be in terms of milliamperes, right? And we saw that earlier that usually this IL would be in terms of kiloamperes. So this is very negligible. So this, I'm not saying that it's equal to, but it's approximately equal to I load, right? So let's look at the first condition. The first condition is during full load condition. During full load condition, right? Uh, Q consumption would be in terms of VARs, right? So Q generation also will be in terms of, it will be in terms of V square by XC, which will be approximately in terms of VARs. So we are talking about the Q generation of the transmission line. It's not, we are talking, so see, the thing is that if you see the transmission line, it has both a component that acts as reactive power consumption and it also has a reactive power generation, right? So we are looking at under full load condition. So under full load condition, since I load, right? I load will be in terms of kilo amperes, right? The reactive power consumed, Q consumed, will be in terms of MVAR and Q generated will be in terms of EVARs. So under full load condition, it acts as a sink for reactive power. So by default, when we say reactive power, we are talking about lagging reactive power, right? So it is going to be a consuming point for reactive power. This is under full load condition. So what we're trying to say is that we are trying to map the behavior of a transmission line under different conditions, right? Now, if you look at the second condition, which is the no load condition. So under no load condition, technically I load is 0. So Q consumption is 0, right? And what would be Q generation? E square by Xc will be in terms of kVArs. So this is now acting as a right, because Q generation is greater than Q consumption. So basically what we are trying to say here is the idea is transmission line has dual behavior. It has dual behavior. So under full load is a sink, and under no load is a source. So you see the behavior basically as the load increases from no load to full load, the transmission line changes from a source of reactive power to a sink of reactive power. Is that clear? Right. So yeah, so let me go back to black. Right. So if you see voltage at, we looked at the equation yesterday, right? Voltage at receiving end is basically is KQ, or K is what? Right. KQ, right? So predominantly the load at the reactive end is going, sorry, at the load end is going to be reactive, and on the top of that the transmission line effect also comes. So at almost all the given times VR is going to be less than Vs. So but the voltage should be maintained with the limits of plus or minus 5%, right? And to do that we actually tend to use the concept of load compensation, where we introduce additional capacitors and ensure that the load consumption is also within limits. But during, again, as we saw earlier, during no load condition, right? Under no load condition, this um, Qgen is uh, Qgen is higher. So under no load condition, net Q is equal to negative. Therefore, VR is equal to Vs minus EQ net will become Vs plus EQ net, right? Modulus of EQ net. So under this condition, what happens? VR would be greater than Vs, and this is called as Ferranti effect. Right? It's called as Ferranti effect. So basically, when you are turning on a transmission line, like when you're introducing a transmission line, at that point, the voltage at the receiving end will become higher, and this will cause the traveling wave phenomenon and all those things, right? And usually, what we do is that when we are actually powering a line, we connect the reactor at the receiving end so that this voltage does not go up. That's where we use reactive shunt compensation, right? So before 1990s, we used to use permanent reactors. Nowadays, we use switched reactors, right? We have a lot of power from devices. Now let's look at transformers, how transformers behave, right? Right. So we know flux, right? So what is transformer? Transformer is basically magnetically coupled device, static device, right? So MMF divided by electric. Have you guys started or completed your uh, electromagnetics, engineering electromagnetics? Is it done? Okay. Oh, electromagnetics is done, right? Cool. So you probably know these concepts already, right? So it is NIA NIQ, Q divided by reluctance Rx, right? Basically, this is V. Then there is the direct axis current, and there is the quadrature axis current IQ, right? And I is basically right, and this is right. So and where L is what? R is L into L divided by mu0 mu r, where mu0 is 4 pi into 10 power minus r. So basically, if you see over here, if you choose the material correctly, right? If you choose the material correctly, mu r will be high, right? When mu r will be high, what will happen? R will be low. And when R will be low, for the given flux, right? For the given flux, you need less IQ, right? So basically, this phi IQ will be less, which makes the phi, this phi, sorry, this thing is called as theta. The angle less means less reactive power burden on the system, right? So basically what happens is that what is Q? Q is equal to VIQ, right? Reactive power is Q VIQ. So if you are choosing the material correctly, which has high mu R, then R will be less, making the IQ required for the same flux to be less, making reactive power to be less. Right? Basically, the transformer is one of those devices in power system that has gone through like probably the best design setup till now. That basically it is the no load current. See, the no load current drawn is 2 to 5% of full load current, right? So basically, what is the purpose of no load current? So the no load current is used to, since if there is no load but some current is being drawn, it is basically to satisfy the reactive circuit within the system, right? To set up the magnetic field. So basically, the react in that sense, the reactive power drawn is almost to 5%, which is small, very small, and is usually neglected, right? Now let's look at the dangers of all circuit machines, which is synchronous machine. So far so good. Have any doubts? Please let me know. Okay? Are we good? I'm audible. I'm audible, right? Okay, great. Okay. Synchronous machine. So basically, if you see, induction machine draws on, it does not have a separate what you call as exciter circuit, but synchronous machine has separate exciter circuit, right? And okay, so if say suppose uh, it has two setups. So if what you call as there will be the stator where we are talking about, and then we have another rotor, right? And rotor basically has the field winding. Basically a field winding, and so there will be I field, right? If I field is equal to I field rated, then flux in the system is flux rated, right? This is called as normal excitation. So basically, the system requires this much amount of flux, right? And the current corresponding to that is IF rated, right? And if the field current in the system is IF rated, then this is called as normal excitation, and this does not neither draws nor supplies reactive power, right? So basically, under normal excitation condition, this one does not participate. Doesn't participate in reactive power exchange. Right? There is no reactive power exchange in the system. Right? Now, and what will be the power factor if there is no net reactive power drawn or supplied? What will be the power factor? Can you tell me what the power factor would be if no reactive power is drawn? So under normal excitation condition, what would be the power factor of the generator? Connected to the unity. So are we done with the slide? Right. Right. Now let's look at the next condition, which is under excited. Right. So what does under excited mean? Under excited means IFS less than IF rated, right? And means phi will be less than rated. But synchronous machine requires constant rated flux, right? So hence it will draw the IQ component or the magnetizing current or the magnetizing current, right? And therefore what happens? Reactive power is so from talking from a perspective or a convention. So if it is synchronous motor, right? If it is synchronous motor, right? It is considered as lagging PF. Why? Because if this is the power system, right? This is how the current flows, and the current flow and the reactive power flow are in the same direction. So if the current flow and the reactive power flow, this is one good way to think about it. If the current flow, so when you're saying load, it draws current, right? So if the current flow and the reactive power flow are in the same direction, then it is considered as lagging PF. So here it is consuming lagging PF, right? And same thing with respect to synchronous generator, it is leading PF. Why is that? This is power system, this is generator. So the current flow is in this direction, but the reactive power flow is in this direction. So the directions are opposite. So hence it is leading perfect. So this is okay. This probably is one quick what you call as check that you can do to ensure how to label it lagging or leading. Like think about it from the capacitor point of view. So capacitor is basically like a passive circuit which actually draws current. So at the end of the day, the current flow is towards this, but the reactive power supply will be in the opposite direction. So okay, we are talking about the lagging reactive power, right? So this will be considered as leading because the current and this one is opposite, right? Now let's look at the overexcited condition, right? So what is happening in overexcited condition? If is greater than rated. So phi will be greater than rated, right? So it has excess of magnetizing current, so that will be fluxes. So it will be injected into the system in the form of reactive power. So it is 9 reactive power, right? So synchronous motor, thinking about from a load perspective, it is giving PFY. So for this box power system, the motor usually draws current, but the reactive power is being injected, so it is opposite, so it is leading. And synchronous generator, it is supplying. Think about it. So this we are talking about supply. Here it is supplying leading PF, here it is supplying lagging PF, right? The current the reactive power must be in the same direction. So it is lagging. Right? So when you're talking about this one, let's look at the circuit. Let's just temporarily put it as E angle 0. And this is axis, and this would be B angle delta. Where what is delta? Delta is the angle between synchronous rotating reference axis and magnetic field. It's not the exactly physical difference between rotor and stator, but yeah, the magnetic electrical equivalent, right? So under this situation, Q is given as V divided by X is U E cos delta minus V, right? So when the condition is basically E cos, since V and X cannot V cannot be zero or X cannot be infinity, right? E cos delta is equal to V. What is the condition? This normal excitation, right? Right. Then E cos delta greater than V. Is this condition? Means Q is positive over excitation and E cos delta is less than V. It is under, right? Mm, just give me a second. Okay, cool. All right. So let me just summarize this. Let's summarize this in a diagram, right? Let's summarize this in a diagram. Okay, just give me a second. No, I'll give you the previous slide. Done. Okay. So let's just summarize this over here, right? That is that. So let's look at. So this column will represent the excitation. So this column is for synchronous generator, right? This column is for power system, and this column is for synchronous motor, right? So we are going to look at three different conditions, right? This is what under excited, right? This is over excited, and this is normal, right? So when you're talking about synchronous generator, under excited condition, reactive power flows from power system to the grid. Here also the power system to the grid, right? And notice the condition E cos delta is less than V, right? So here power factor would be leading, the power factor would be lagging. Here also E cos delta is less than V, right? Reactive power is flowing here. Under overexcited condition, reactive power is flowing here. So here Q, here the power factor would be lagging, and E cos delta would be greater than V. Here also Q is being supplied. Here the power factor would be, however, leading, and here also E cos delta would be greater than V. And under this condition, there is no reactive power flow, right? So here PF would be unity. Also power factor would be unity PF, and E cos delta would be 0, Q would be 0, right? Is this clear? Can I move on to the next slide? All right. Let's start. Okay. So what we saw here was that a synchronous generator can act as a source or a sink for reactive power, right? Mostly we need it to be a source of reactive power. But technically, strictly speaking, we should not use it because mm, we do use it to some extent. But strictly speaking, synchronous generator is for what? Reactive power. Synchronous generator, we need to use it for active power. Why? Because there is only so much MVA that the system can generate, and P square plus Q square. So if S is kind of given system size, machine design and all, the S is fixed. So if Q is, say, suppose 0, then we get ES, which is P max. So if you have to supply reactive power, right? If you have to supply reactive power, the effective P supplied comes down, right? So we tend to, what we do is that we tend to operate the system higher in 9.5, between 9.5 lag and 9.5 lead. And we also, for this, maintaining this, we say that the reactive power in the system of a generator should be within the limit, right? So it cannot consume more than Q max, and it cannot, sorry, it cannot consume more than Q min, and it cannot supply more than Q max, right? There is also one more justification for why we should not use synchronous generator as a manipulator of reactive power. what happens is that if suppose you want to supply it as a make it work as a generator, right? What happens? IF will be greater than IF rated. What does that mean? It means I square F RF will increase, which will cause heating. Heating also increases, and cooling of a rotor is not easy, right? We have to so it's a very compact system, and cooling it is not easy, right? So it may cause breakdown. So therefore, do not be thinking about that, right? So if you remember when we started talking about reactive power compensation, we said voltage control. We said that there are two methods. One is internal method, and another is external method. Internal method is by using the excitation of the generator, and this is one of the reasons. These are the reasons why we do not prefer to do it, right? Also, like if under the conditions, suppose if IF is less than IF rated, right? IF is less than rated, what happens? EF decreases, and if EF decreases, the stability limit EV by excess also decreases. So we don't want that also to happen. So what we usually do is that we tend to employ external devices. So we employ external devices like synchronous condenser, then capacitor, then fax devices like SVC, com, etc. Right? Is this clear? Are you guys with me so far? Okay. Okay. With this, I think I'll stop this topic and we will go to the next topic, which is load flow, right? To be so, give me a second. Give me a second. Masha, കുറച്ച് വെള്ളം എടുത്തരോ വെള്ളം. Yeah. Now let's look at the concept of load flow, right? Right. So, what do you know about load flow? Do you remember what I used a very specific phrase during our initial discussion? You remember what that was? So basically, what load flow? You remember what that is? I told you that it is like taking a picture. It's like taking a time frozen snapshot. Latest time frozen snapshot. The power system, right? Basically, what it does is that it actually gives the solution of the network. What does solution of the network mean? It means the values of all the parameters that we are interested under the state condition. Okay, so it can be under constraint, under network constraints, and these constraints can be what can these constraints be? Which these network constraints can be, basically it can be nodal voltages. These are the values that we are studying: nodal voltages, real and reactive power, right? And reactive power. Then it could be settings of transformers. Setting of transformers. Right? So basically, what we are interested in when we're looking at load flow is the parameters is the voltage at every nodal voltage, and the phase angle, right? The power active power injection and the reactive power injection, right? So what we do is that we take, so at the end of economic dispatch or at the end of unit commitment economic dispatch, we will get to know what the P and Q values are for different generators, right? So we say that, okay, this is the P, this is the Q values, right? And then we want to find what is the voltage, angle, and power and Q at all nodes. So one of the assumptions that we are assuming over here is that, so the assumption is we know the network model parameters. So the resistance, reactance, and admittance, inductance, and everything is known, right? So that is the assumption over here. Is the assumption over here, right? So as I said, here in the system, the node is called as, also called as, also is same as bus. So a bus and the node is the same, right? So what are the steps involved in load flow equations? So the first one is formulation of network equations, right? Second one is solving the network equations, right? So we will choose different methods and then we will solve. So when we are looking at load flow, I said bus, right? So we have four quantities, right? I told you, like we have P, Q, B, and delta. So at any given node, we tend to know max to max two variables. So we know two values, don't know two values. So based on this combination, we have three types of buses, right? The first bus type is So this is known or specified. This is unknown or quantities to be obtained. So are you guys familiar with this? So there is load bus and there is generator bus and there is that bus. Do you know what is known with respect to a load bus? Can you fill this table for me? I put this as 1, 2, 3, 4, 5. Yeah, can you fill this for me? What are 1, 2, 3, 4, 5, 6? Are you familiar with this? If you are not familiar, just say no in the comment section. Goodness, PQ. Good. So this is PQ. The other one is V delta. And with respect to what is 3 in area? So the assumption every point is that we know P. Let us put it simply, but yeah. Here it is. We know the assumption is that we know PV. We don't know Q delta. And this is lag versus P delta. And oh, sorry, that lag bus we don't know P. So here we know P delta, and it is V. And do you know what phi is? V delta. Right? Is that clear? Okay. Can you move on to the next slide, or are you done taking this down? Right. Right. So now let's look at how to formulate. So we told in this step, right, that we have to formulate the network equations and then we have to solve it. So let's look at how to formulate it. So anyway, there are two approaches, like when we are trying to solve this one, right? One is node frame reference, node frame reference, and second one is loop frame reference. Basically, it's the difference between KCL and KVL, right? In node-based reference, we use KCL, and in loop-based reference, we use KVL. Given the ease of formulation and computer memory and processing time, we tend to usually go for nodal frame reference, right? So let's look at a 3-bus system. Is this clear? Why? So this there are two references, right? So here we are going maybe once I write the equation will be clear. Right. So we have three buses. It's either one, two, three. So let's assume there was generation and loaded all three buses. This is V1, V2, V3, right? And the current injected is, we are assuming this connect generator convention. So this is I1, V2, this would be I3, right? And we have currents flowing in here, right? So the current flowing, okay, also the network equation. So this would be Y12, this is Y23, Y23, and Y13, right? And the current flowing through this lines would be, we have I2 and I12 would be is equal to minus of I21, right? Similarly, we'll have I13 and I31, and also I32 and I23. Also, we may have some sort of power consumption at that one particular node, right? In any node, there might be some sort of its own power consumption, and that would be I11, I22, and I33. Right? So is this setup kind of, we have put in a lot of terms, but I think it's fairly straightforward, right? Is this clear? Right? Have you taken this down? Okay, cool. So if we go with the KCL, we are going to again end up with our Y bus, right? So what would KCL mean? KCL, if I take KCL, it means I1 is equal to I11 plus I12 plus I13. Similarly, I2 will be I22 plus I23 plus I21. Right? Similarly, I3 would be I33 plus I31 plus I32. So if I just put it in terms of I11, it would be V1 minus V2 into Y12 plus V1 Y11 plus V1 minus V3 Y13. So if you rearrange this, you will get Y11 V1 plus Y12 V2 plus Y13 V3, right? So similarly, you can go and find for I2 and I3. You will get the same thing. So you will get I1, I2, I3 is same as I11, I12, I13, I21, Y22, Y31, Y32 into V1, V2, V3. So this is where we learned Y bus space of, right? So y1, y1, y11, y22, y33 are called as the total self-admittance, and they have strong higher magnitudes than the other one. And since it's symmetrical, we can just store the top half and we can save a lot of memory. Earlier days, see, nowadays it's fine, but in earlier days, there was severe memory constraint on the system, right? So people thought about a lot of ways on how to conserve memory, right? So let's just, before we proceed, let's just also summarize. How does the current equation look? P is equal to Q is equal to 1 to N by PQ, right? What happens is that, so just let's summarize what we kind of looked at in pi bus earlier, right? As the number of bus increases, a lot of the interconnectivity becomes less, and a lot of half diagonal elements becomes of the off diagonal elements becomes zero, right? But if you add inductive element to the system, the y11 would become stronger or will become bigger, and if you add a shunt element, this y11 will become smaller. We saw all these things, right? Right. Yeah. So now let's look at how do we solve. Now this is basically the equation, right? Now let's look at how do we solve it. Okay. So the first, so basically problem is that we are looking at, see, it looks very simple and straightforward, but we are looking at a no, non-linear equation, set of non-linear equations. And usually to solve set of non-linear equations, we tend to use iterative methods, right? So the first method that we are going to look at is called as the very famous Gauss and the Gauss method, right? So let's look at first one as load bus. So in, I think, right? So in Gauss method, let's look at load bus. So what is the thing with load bus? We know PP, QP is known, mode VP and delta P. So again, you see, when you're talking about complex term, we can represent it in two ways. Right? We can represent, this is the polar representation. We can also represent it in the rectangular form, that is A plus JB. Right? That is again to increase the number of variables. So we tend to prefer to go with polar components. Right? So current at, let's look at the current at bus P. Right? What is current at bus P? IP is given as sigma Q is equal to 1 to N by PQ PQ, right? So I can just write this as YPP PP plus sigma Q is equal to 1 to N YPQ Q, where Q is not equal to P, right? So I write this, rearrange this. YPP VP is IP minus is equal to 1 to n not equal to e by pq vq, right? And I can express finally vp, right? Finally, we don't know vp, right? I can express vp as 1 by pp ip minus q is equal to 1 to n not equal to p vq. Now you want this, right? Okay. All right, right. So okay, we did this, right? Now we know sp power at sp is pp pp conjugate, right? So since ip we are going to replace ip, uh, what we what we rather do is that which is this is equal to pp plus jqp, right? So instead what we do is that we take pp conjugate ip. What would that be? It would be qp. And what does that mean? ip is pp minus qp divided by pp conjugate. So finally what happens is that if we substitute that in the equation, we get pp is equal to 1 by pp into pp minus jqp divided by vp conjugate, right? Minus q is equal to 1 to n not equal to p by pq vq. So here we have a choice. We could represent vp in its complex form where vp is a plus ib or ri theta, right? R angle theta. So we can prefer this. Or we could also go, okay, so we also say then that by mod vp is equal to root of a square plus b square, or and delta is tan inverse b by a, which is theta. There are two options of representing how we are going to represent, right? Right. Are we good so far? Is this clear? Is it so far okay? Okay. So now let's look at the next bus, which is generator bus. Right? So in a generator bus, what is known? Vp and delta Vp is known. What is unknown? Qp and delta P are unknown, right? So again, going by that older logic, what would be this P is V conjugate I is Vp minus VQP, right? So this is same as Vp conjugate into sigma Q is equal to 1 to n by PQ PQ. So V conjugate into I, right? So if I say one of the things that we don't know is QP, right? QP is what? Imaginary part of Vp conjugate, negative imaginary part of Vp conjugate, right? And we could solve for Vp, again the same equation, 1 by Pp into that same equation we derived earlier, right? Vp minus AQP divided by Vp conjugate, right? Minus Q is equal to 1, Q not equal to P, n by PQ, PQ. And here we only go for this is A plus IB. Since we already know the magnitude of Vp, we use this equation only to solve for delta P. What is delta P? According to this, delta P would be tan inverse P by A. Is that clear? That is basically generator bus. Now last but not the least, we have to find for slack bus. Right? So what is known? You know Vp and delta P. What is not known? Vp, Vp. Right? So what we do is that we do the power balance, right? So when it comes to slack bus, we find P as sigma Pg minus sigma P load, right? And Q, the slack bus is Q Pg minus sigma Q here. Generation load, the difference. Am I audible? Am I audible? Right. Audible, right? So far so good. Right. Now let's look at how do we iteratively solve, right? You see this equation that we have formulated for Vp, right? It has both Vp, right? So the iterative method is that we substitute the old value and we substitute a set of value to find new value. Then we will take that value and substitute again till we converge to the value we want, right? It's basically a recursion process with a breaking condition, right? So let's look at the algorithm, right? So first one, we assume flat voltage. Flat voltage is assumed. So what does flat voltage mean? All VP, all voltages in the system are 1 plus J0 or 1 angle 0, right? Then step 2 is to set the convergence criteria. The convergence criteria. So the change in voltage from one iteration. So we calculate voltage for all the buses. So from one iteration to another, if we take the differences for all the buses, the maximum should be less than sigma, where this is a pre-specified value. Right? So then step 3 is basically we have to have an iteration count. Iteration count is set as 1, right? And step 4, we set the bus count as 1. Now we start the actual algorithm, right? So first is check, is it a slack bus? Right, we check it slack bus. So yes, if it is yes, we say go to step 7. There is no 6, right? Now what is step 6? So it's not a slack bus. Assume it's not a slack bus. Then it is a load bus, right? So one thing about Gauss method is that it does not treat generator buses separately. It takes both generator buses and it treats both generator buses and load buses the same way. We treat it as a load bus. So if it is a load bus, right, what we have to do is that we have to calculate voltage at bus P for A type machine, right? So how do we calculate that? We calculate Vp eighth iteration is 1 by ypp into pp minus jqp, we know these values, right? Divided by vp of a minus 1 iteration conjugate minus 2 is equal to 1 to n, q not equal to p, y pq v q, but a minus 1 iteration, right? And then we calculate delta vp as vpk minus vp minus 1, right? Now the next step, seventh step would be, once we are done with, say suppose the first one, the iteration would be check if is equal to n, that is the bus count, right? Yes, if it is yes, means all bus has been calculated. Right, all bus has been calculated. So we can go to next stage. It is no, that means it's not, all buses not covered. Then what we do is that we increase p is equal to p plus 1 and say go to step, right? So, so what happens is that if this, until this n becomes, it acts as a loop, right? And once that is done, at step 8, what do is that we check for convergence criteria. What is convergence criteria? Delta P max less than epsilon. So we check if we have calculated delta Vp for all the buses, right? So if it is less than epsilon, so if yes, it is convergent, or we have got our solution within our range. So therefore, stop. Right? If no, what we do is that we again increase the iteration count, k is equal to k1, k plus 1, and say sure. Right? So usually what happens is that we also have to add a we also need to add a condition to check for k. So that, see, sometimes what happens is it will never converge. So usually in practical programming, we also add a condition for the yeah. So we also have a practical condition, right? Done. Okay. Yeah. So here we have, so this is basically, and we keep on, we follow this 8-step process, right? Uh, but this has a lot of, we never use Gauss method because it has a lot of disadvantages, right? The first one being, we don't treat load bus and generator buses separately, right? All buses are treated as load bus, which is not good, right? And it is low convergence. The convergence rate, we have to go through something like 10 to 15 iterations. Also, low convergence implies time taken for convergence is high. It takes a lot of and one more problem is that if you see here, if you're when you're calculating the VPK for the current iteration, we use the previous iteration's voltage, right? But suppose we are calculating for the 100th bus, right? We have new voltages for up to the 99 bus. So we could actually use that, but instead we keep on using the old value, right? So basically old voltage profile is used. Right. So what we do is that To overcome all these disadvantages, we tend to use something called as right. We tend to use something called as Gauss-Seidel method. So step 1 to 4, same as Gauss-Seidel method. Same as Gauss method. Right. So let's look at what that was. So we assume a voltage, we set the converse criteria. So all these steps are same as the Gauss method, right? So let's look at what is the difference, right? So at step 5, you're done, right? Step 5. So first one is check a slack bus. If it is slack bus, you say go to step 8. And if it is no, we say step 6. We check if it is slack bus. If it is slack bus, we say go to end. If it's not slack bus, we proceed, right? So then we check, is it a generator? A PV bus or a generator bus, right? If it is no, you say go to next step. Please skip whatever is being done here. Yes, then say calculate QP and VP. Right? What is the Q? What is QP? We calculated as QP of K is equal to imaginary part of okay. All right. Sorry, give me a second. Yeah, sorry. VPK, this formula we derived earlier, right? VPK minus 1 conjugate into Q is equal to 1 to N YPK VK K minus 1. We can calculate the QPK value like that and then calculate VPK as 1 by YPP into PP minus JQP divided by VP of K minus 1 conjugate, right? One second. Okay. Minus 1 plus sigma Q is equal to 1 to P. So y pq pq k plus q is equal to that plus sigma q is equal to plus 1 to n y pq p q q minus, right? And from this one we will calculate tan dpk k, right? Then step 7, in 7 means it is a load bus, right? We came here, so it means it is a load bus. So we say ppkk is equal to 1 by ypp into pp minus aqp divided by ppk minus 1 v conjugate minus, did I put minus over here or plus? It was wrong. You guys not correct me. Minus, yeah, minus sigma q is equal to 1 to p minus 1. Should not 0, that should be p minus 1. So for all the buses up to that bus, we use value calculated in that iteration minus plus 1 is equal to plus 1 to, and we use the value from previous iteration, right? And then we calculate and step 8 mass and step 9 mass 8 first method. We check if all the iterations are complete, and once we have all the iterations, then what we do is that we calculate the slack bus power and reactive power, right? Also, what we can do is that in order to make the iterations further faster, we use something called as an acceleration factor, right? So acceleration factor, what we do in acceleration factor is that in step 6 and step 7, right? Step 7, we add one more 7d, one more additional steps, where we say after calculating v p the accelerated version is whatever vp a minus 1 we calculated plus alpha into VPK minus this is called as acceleration factor, right? And this is a very arbitrary mathematical approach, right? So we usually tend to use alpha as 1.6. Is that clear? Over on the previous slide. Okay. Okay. Now see here we improved upon certain situation conditions where we are treating load bus and generator buses separately. Then we are also using the latest updated values of uh, system value voltages, right? But there is also one more condition that here, if you see, we are not putting any constraints on reactive power. But we saw earlier that reactive power of a generator is constrained, right? So we have to consider the constraint Q. What is Q? QP is less than or equal to QP max less than or equal to QP min, right? So what we do is that in step 6, right? So we do step 6. For calculating QP. So here also we can actually use the updated voltage, right? Where we can say QP is imaginary part of negative of imaginary part of VP conjugate or VP conjugate. So this one conjugate to Q is equal to 1 to P. Here we use 1 to P only. Uh, yeah. Uh, yeah. So this is equal to 1 to N by PQ PQ. We can do also that we can split it also where we up to P we can use K minus 1, sorry, K up to P minus 1 we can use K, and P to N we can use this one. That is fine, right? And we check if so we have this additional check where we say if QP K is less than Q min, right? Then it is not possible, right? It is divergent. Then what we say is that QPK is set to Q min, and for this step we will assume that it is a load bus. That means we will also update the VP value, right? And if it is no, right, then we say yes, QP is greater than QP now. Now we check if QP is greater than QP now. Yes, then we say QPK is to max, and we treat it as load bus where we just don't update the angle, we also update the and if it is no, This is fine. So we just calculate. We fix the VP value, right? So the idea is that if the reactive power constraint is violated, then we treat the bus as a load bus. If it is within the limit, we treat it as a PV bus. Is that clear? Okay. Now let's look at a problem, right? So there is bus, and we are given power, right? So 1, 2, 3, 4. So we are saying that we don't know the real power and reactive power. Then we do this as 0.4, 0.4, and 0.1. So we say 0.5, unknown. This is 0.6, 0.3, right? So we say that the reactive power, so this is given. Question is reactive power is calculated P plus 0.25 U, right? If network is lossless P and Q at 1, we calculate. So this is 0.25. This has been calculated as 0.25 per unit. So can you calculate and tell me what is P1 and Q1? Given system is lossless. Let me know when you're done. So do you know how to calculate or do you want me to solve? Mm, okay, but still. Okay, all right. So let's look at the given situation, right? Okay, so for bus number one, we don't know neither P and Q. So what is this? This is the slack bus. Here we know both P and Q. So this is load bus. Here we only know P, right? So this is a generator bus, and we know both P and Q. So this is a load bus, right? So what did we find as slack bus? It is sigma P generation minus sigma P load, right? So how much is generation? Oh no, sorry. Sigma P load minus sigma P generation. Sigma P load minus sigma total load minus total generation, right? So how much is this? How much do we have total load? See, zero point 0.6 and zero point 0.4, right? So we have load of 0.6 plus 0.4, right? Minus we have an existing generation of 0.5. So basically what we are saying is that we have a total load of 1 per unit and zero point 0.5 is already being supplied by 3. So whatever is left needs to be supplied by slack bus. So this is 0.5 per unit. And now what have they said? They have calculated Q1, right? What is Q1? Q1 is given is 0.3, 0.1, and they said that they have calculated it as 0.25. Okay, so basically it is 0.3 plus 0.1 minus 0.15, 0.25. So it will come as 0.15. Is this clear? So there is one more extended second part of the question. If system has loss of P loss is equal to 0.2 per unit and Q loss is equal to 0.05 per unit. Q1 is equal to Q1 is equal to, right? So basically what does slack bus do? So each generator has fixed generation. So whatever is excess is basically picked up by slack bus, right? So what will be P1 and Q1 in this case? Mm, P1 would be whatever it is already had to generate, plus it also has to supply for the losses. In this case, it would be 0.7 per unit. And Q1 would be how much reactive power it has to generate, plus also the losses. Is that clear? Okay. Let's look at, okay. Let's look at one more problem, right? we have a 3-bus system. Okay. This is 0.04 plus G 0.06. This is 0.02 plus. So we are given the per unit impedances of this, right? We are ignoring the shunt susceptance. Okay. So PU impedances is given. Susceptance is ignored. Then we are given one is flag bus, 2 is load bus, and 3 is generator bus for the PV bus, right? And we are also given V1, the value as 1.05 into 0. Then we are given P2 plus Q2 is 8.96 plus 8.46, right? And we are given P3, modulus value of P3 as 0.02. So we are asked to calculate voltage at bus 2 and Q at bus 3 for one iteration. Let me try. What do you want me to solve? Let me do something. Let me solve this one for you. Right? Otherwise, this will take time. I don't think we will be able to finish in time. You can solve this along with me, right? So what we are going to do is that we are going to assume, what is the first step? We need to assume the initial voltage. So we are assuming this is angle 0, and V30 is, we know the magnitude, right? You can solve it on here, but just solving here, right? 1.2 angle 0, right? Z12 is given, so we can calculate Y12 as 7.69 minus J11.3, and we can calculate Y23 as 15.38. You just look at now and you can try to solve it later also. Okay, you should try this on your own by hand, right? Once. So we can calculate the Y bus. Right? We calculate the Y bus. If you come as 7.69 minus J11.3 minus 7.69 plus J11.3, right? 0 minus here we have both coming right. So 23.07 minus J34.61 and minus 15.38 plus J23.07, right? And this would be 0, and this is minus 53.8 plus J23.07. Here 15.38 plus J23.07. So bus 1 is slack bus, so we don't do anything. Then we go to bus 2, right? Bus 2 we can calculate V2 dash 1, right? V2 dash 1 is 1 by 23. So the value y22 we can calculate the one from this thing. Then minus 5.96 plus a 1.46. So why does this sign change? Because this is a load, right? So the effective current power injection would be minus. This would be minus of minus 1.4 will be plus 1.4 divided by, we have taken the current voltage is 1 minus 1 plus J0. So the conjugate is 1 minus J0. It shouldn't matter, right? And we can say this is minus y21 V1 plus y23 V3. 0, this is 1. So if we substitute the values, we will get it as 0.921 minus 8.1, right? And at bus 3, we calculate the reactive power as 3 dash minus imaginary part of substituted values, right? It will be 1.02 into 0 into V1 dash plus the values. If you substitute, it will be y12 V2 plus y13, sorry, y31 y33 v3. Substitute, you will get this as 0.86 per unit, right? So we have to try few more problems, and we will continue with we'll start the next session with few more questions, and then we will look into Newton-Raphson method in the next class, right? Right. So I am stopping over here right now. Do you have any questions? Okay. So yeah. So see you in the next class.